We're trying to get to a point where instead of having to deal with linear maps directly, we can instead deal with the matrices that represent those linear maps. And that's worked okay so far because we've seen that this rep map is a homomorphism between the space of linear maps from V to W to m by n matrices, right? We know that this is an isomorphism, but there's actually, right, the operations that live in this vector space of linear maps are addition of linear maps and scalar multiplication of linear maps. But there's actually another way that you can combine linear maps that doesn't exist just in this vector space, and that's composition of linear maps. Right? Linear maps are functions, and so you can compose them as long as their domains and codomains line up in sensible ways. So maybe the first thing to check about composition of linear maps is that a composition of linear maps is itself a linear map. Right? That would be a good thing to know. If a composition of linear maps turned out to not be linear, then of course we'd have to stop doing linear algebra at that point because we would have a function that isn't linear. So suppose we have a linear map from V to W, let's call it H, and a linear map from W to U, call it G. Then their composition goes from V all the way to W, right? So the picture you should have in your mind is like this. H goes from V to W, and G goes from W to U, and so U. And so the composition goes from V all the way over to U. And remember, the composition is defined like this. G composed with H applied to a vector is G of H of V. So let's check that this is linear. Remember, to check this, all we have to do is check that it preserves structure. So if we have, say, AV plus BW, what do we get? Well, this is, just by definition, this is G of H of AV plus BW. But H preserves structure, right? We're assuming H preserves structure because it's a linear map. So we can use that to write G of AH of V plus BH of W. But remember, we've assumed that G is a linear map, so G preserves structure. So this is AG of H of V plus B times G of H of W. But of course, this is just the same thing as A of G composed with H applied to V plus B times G composed with H applied to W. And so this shows that, yes, indeed, G composed with H does preserve structure. So a composition of linear maps is itself linear. And what that means is that the composition linear map has its own representation. And what we would hope is that somehow we could take the representation for G, the matrix that represents G, and the matrix that represents H, and somehow put them together in some way to get the matrix that represents the composition. That would be the best thing, because then we could compose linear maps only using their representations and not have to deal with the linear maps directly, which would be ideal. So let's think about that problem. How could we actually do that? So we'll have this H and G like before, but now we have to talk about representations. We have to choose bases for our vector spaces. So let's say B is beta 1 through beta n, and that's a basis for V. C is a basis for W. Let's call that, I guess, gamma 1 through gamma, might not be n, I guess, m. And then for D a basis for our third space, U. I guess delta would be the next Greek letter to use. So how about delta 1 through delta, I don't know. I need a subscript. I've used m and n, so now I'm out of a good subscript. How about P? Is it going to cause a problem if I use P? I don't think I've used P yet. Okay, so what we need to do is compute the representation of the composition and see if we can somehow interpret it as some combination of the representations for the original maps, H and G. Okay, so the setup here is we have V, we have a map H that takes us to W, we have a map G that takes us to U, we have rep B, which takes us to Rn, we have rep C, which takes us to Rm, we have rep D, which takes us to Rp, and then along the bottom we have matrices. So this is rep, I guess we usually call this capital H, I guess. This is the matrix that represents little h, so this is rep BC of little h. And then going from Rm to Rp, we have rep CD of G. And I guess we could call this capital G. Okay, and then just to have notation for what these matrices are, I'm going to call the entries of the matrix H, Hij. So keep in mind that there's actually, right, this matrix is actually m by n, and then capital G, I'm going to call its entries Gij. And careful about this, there's nothing in the way this notation is set up to tell you that these matrices have different sizes. They do. This one is m by n. This one is p by m. Okay. So we have written down what the representation is for H and G. What we need to do is calculate the representation of G composed with H. So how do you find a representation? Well, you start with, you hit each basis element over in V with both maps. So do beta 1. You hit it with both maps, and then do the representation and see where we end up down here, right? So, but the thing is, we know that this way around this square is equal to this way around that square, but we know that that's equal to this way around this square. And we know that the upper side and right side of this right-hand square, it gives you the same result as going down and then right. So to go across, all the way across the top and then down, instead we can go one step to the right and then down and then across, right? Because we know that we've only changed this right. We've used what we know about this right-hand square to switch. But now we can use what we know about the left-hand square. Instead of this zigzag path, we know that we can find what happens to beta 1 by going down and then across twice. Right? We know we're going to end up in the same place because we know the different paths around this diagram all give us the same thing. So that's going to be easier to figure out because then we can use these individual matrix representations. So what happens to beta 1? Well, when you do rep B of beta 1, what you get is 1 and then a bunch of zeros, right? Okay, and then what happens when you hit that with the matrix H? Well, if you look at the matrix, if you imagine the matrix H multiplying it by this, with a 1 just in this position, it's just going to pick up the first column. So this is going to be H11 down to M1, like this. And now we hit this with the matrix G, right? We do matrix multiplication, we do the matrix product G times H11 down to HM1. Okay, so what do we get? Well, it's not going to be pretty, but we can definitely write down what it is. So it's going to be G11 times H11 plus, and so on, down to G1M times H, right, times the last entry in this vector, which is HM1. Right? Notice that how this indexing is working is that these adjacent indices stay equal as you go down this sum. So this was G11 H11, then it's going to be plus G12 H21, and so on, all the way down to G1M HM1. Okay, and then what's the next row? Well, the next row, the h's are going to stay the same because, right, we're sticking with this one vector h. But what's going to change is the g's, right? The row index is going to increase by 1 when we go down 1. So the first one is going to be G21. So G21 H11 plus, and so on, down to G2M HM1. And again, these adjacent indices, right, these inside indices are matching as we go down this sum. And then so on down every entry here to G, how many rows does G have? P. GP1 H11 plus dot 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 down to GPM HM1. And, you know, as before, the inside index matches as you do this sum. Okay, so this is what happened to beta 1 as we did this. So that means this is the first column of the representation with respect to BD of G composed with H. Okay, so what are the other columns, right? We need to know all of the columns. Well, let's do this same calculation, except instead of B1, let's use BI. Okay, so what happens to BI? Well, BI, when you do the representation with respect to this basis, BI is just the matrix of all zeros, except there's a 1 in a single spot. Which spot? Well, the ith spot. So this is in position I. Okay, and what happens when you multiply, when you do the matrix product of H times this matrix that just has a single 1? Well, this just sort of picks off the ith column of H. So this is going to be HI1, yes, HI1 through sorry, H, no, I have my indices backwards. Sorry. So H1I through HMI. And you know what? I'm going to want this index to be J. So up here, instead of I, let's do J. So this 1 is in position J. So this picks off the jth column of H. So we get that. H1J through HMJ. And now we have to multiply this by G. Right? Multiply this vector by G. So G times H1J through HMJ. What do we get? We get, so first row is, right, G11 times the first entry here, H1J, plus, and so on, down to G1M HMJ. And notice, just like with the specific case that we worked out with beta 1, this inside index is matching as we do this. Okay, and every row is going to turn out similarly. The only thing that's changing is the row index, which the row index is on G, right? So G, down to GP1 times H1J plus dot 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 down to GPM HMJ. Okay, and as usual, the inside index is matching as we go down this sum. Okay, so this is the jth column of rep BD G composed with H. Well, you can see that the entries of this column, all of the general form of this column of the representation of the product, it looks generally the same no matter what column you're on, right? It has the same form. The only thing that changes as you change columns is the index on these J's, right? So to get the matrix, the representation matrix, you just put all of these things in one big, you put all of these individual columns in one big matrix, and the only thing that changes from column to column in the big matrix is what J is. And notice that as you go down rows, the only thing that changes as you move down rows is the index on your G's, right? So one nice way to say what exactly rep BD G composed with H is just to say what is in the jth column and the ith row. So what's in the jth column and the ith row is our row index is I, so that's going to be the row index for G. So G I1 times H1, and then the column index for H is the column that we're on. So J plus dot 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 down to G I M HMJ. Okay, so this is the ijth entry for this product, or for this representation of the composition. And as you move to other entries in this representation matrix, you just get this exact same form, except I and J are going to change because you'll be in a different row and a different column. So we have a formula for the representation of a composition in terms of the representations of the maps that we started with, right? Remember, these G's and I's are all coming from the representation of H and G to begin with. So what we will do is we will define, right? We have these two matrices G and H. We're combining them to get the representation of the composition of G and H. So we will define this big messy matrix to be G times H. Okay, so what we're doing is defining a matrix product. And we have defined it so that the product of the matrices represents the composition of the original linear transformations. So we've defined a matrix product. So let's sum up by looking at the basics of this matrix product. Exactly what did we define? So when you have two matrices, A and B, or G and H, or whatever they are, the product A times B, its ijth entry is AI1, B1J, right? The row index becomes the row on your left-hand matrix. The column index of your entry becomes the column index on your right-hand matrix. And the inside entries stay the same as you do this product and sum. Okay? A nice way to think about this is as a dot product. So to get the ijth entry, you take the ith row of the left-hand matrix, the jth row of the right-hand the jth column of the right-hand matrix, and do the dot product of these two. So first times first, that's here. Second times second, that's here. And then all the way up to last times last, that's here. And then you add those together. All right. So we have specifically defined this matrix product so that the representation of a composition is the product of the representations. So we have defined matrix multiplication so that a multiplication of matrices is the same as the composition of the corresponding linear maps. All right. One thing to be careful about here is if you have this picture in mind, which you should have this picture in mind, if we call this the representing matrix here H and the representing matrix here G, you might think that this matrix product represents the composition, but it's not this one. The order actually switches. Okay, so the order that you need to multiply matrices in is the same as the order of the composition that they represent. So G times H represents the map G composed with the map H, right? And just because we write functions on the left instead of on the right, function composition looks backwards compared to this diagram. So just be careful about that, right? But the matrix multiplication is in the same order as you write the functions. It's just the opposite order as you draw this diagram.